Hello. Hello. Hi.
Hello.
Hello. Welcome. Rafael is coming. Here it is. Hello, Rafael.
Hi. How are you?
Fine. 1 second. Oops. Yeah. I was just trying to make the share screen and someone. Oh, yes. Great. So we are already on YouTube.
All right.
People are coming, so let's wait 5 minutes. Do you want to put your
Yeah.
presentation? Tomorrow I have a Japanese exam. Learn Japanese. Yes, Japanese, but the very basic. It's very hard.
Is it? I have no clue.
Yeah, well, I'm afraid me too. Very little. I'm the worst student in the class.
Do you see my mouse on the screen?
Yes, we do. We do.
Good.
Okay, so the people are getting here. The one they're here, do you have any question for Rafael? You can take the opportunity. There were still a small group. Yes, someone asked me if there is a book, a reference book. I told your class notes, but is there another, actually it's Virginia asked me, is there another reference book beside the one that you suggested about algebraic topology? Yeah.
Yeah, there is this Frédéric Chazal et Bertrand Michel. I put it in the chat.
Yes, the one that you mentioned the other day, no? This one?
Yeah, I think I talked about it already.
Yeah, you talked to me, but we haven't. Okay.
Yes.
So, hello, Kama. Some people can.
This one's a good one.
So, Virginia, Rafael is suggesting this reference. Hello, Virginia, are you there?
Yes, hello? I'm here.
Yes, so he's suggesting this reference. You asked.
Yes. That's the one from last time, and I couldn't. I had looked at it and it looked really good, but I couldn't find it again after my computer, restarted. I didn't have it, so I need to somehow save it. I need to save it somewhere.
Yeah, you can find it on archive.
Okay.
Just type this.
Great. So thank you, Rafael.
It's on the chat also.
Hello, Nancy. Hello. Hello. I'm still, by the way, I'm hosted in Université de Namur in Belgium. So it's really a traveling school. So I guess that we can start recording. So we have once more the pleasure to have Raphael with us for another great lecture, I'm sure. And just to remember that Raphael is French, but he loves so much Brazilian culture, music. He's a musician himself. And so please, Raphael, the floor is yours.
Thank you, Stefanella. So, third lesson, we made it to persistent homology, at least.
They are asking you which kind of music you play.
I play chorinho, samba no cavaquinho e no bandolim, logo.
We have to, when I come back, I want to come to the show. Okay, so please go ahead.
So let me give you a brief recap. I introduced the first lesson, initial ideas of algebraic topology, and in particular topological invariance. We've seen in particular homology, right? Simplicial homology, that is a homology of simplicial complexes. And I talked a little bit about singular homology, that is the homology of topological spaces. And we ended this last lesson with the problem of homological inference, right? The problem can be stated as follows. We are doing a scientific experiment and we get a point cloud X, a finite subset of the Euclidean space.
This meeting is being recorded.
And we wish, we suppose that there is some underlying shapes and underlying manifold. We wish to estimate the homology groups of this unknown shape, right? In this case, this point cloud is seen as a sample of the circle. And the strategy I explained last time was in two steps. First, you will select a thickening, right? So we have a whole family of thickenings, xt. And at some point, the thickening has the homotopy type of the circle. It can be deformed, right, onto the circle. So you have the homotopy type of the underlying object, and so you just have to compute its homology groups, and we can do that with the check complex, right? Or a variation of it that we use in practice, the Ribbs complex. And I also explain that this selection of the parameter t is complicated, and there are some cases where it does not even make sense to statistically ask for this parameter t. And so the solution to this problem in let's say computational topology is to not try to choose only one value of t, but choose all of these values. And persistence theory will help us to build from all these values an algebraic object that is called the persistence module, and that will allow to do homological inference. So there are two foundational results in persistence theory: the decomposition of persistence modules and the stability, right? So I will present both these theorems, and I will close the session with a few examples of applications of TDA. All right. So let's start with decomposition of persistence modules. So the notion we will need is the notion of functoriality. I explained last time that homology, so this is an operator that takes as an input a topological space and gives a vector space, right, the homology groups. But it also allows to transform maps. If I have a continuous maps between topological spaces, I can transform the map in the world, in the linear world, so I obtain an induced linear map between vector spaces. So if here this is written for a singular homology, right? Because I consider topological spaces. But for today, we will consider simplicial complexes, right? This is a structure we use in practice. And so the theory of homology we use is simplicial homology. Simplicial homology transforms simplicial complexes into vector spaces and also maps. But what is that map between simplicial complexes, right? There is a notion of simplicial map that mimics the idea of continuous map. And the definition is really simple. I have two simplicial complexes with sets of vertices Vk and Vl. A simplicial map. So this is a map between the sets of vertices, such that the image of a simplex is a simplex, right? If I take a simplex of my first simplicial complex, then its image, defined as the set of images of all its vertices, must be included in L, right? So I give an example here. K is this segment, is written here. L is the triangle, and the map F is this one.
Aula aqui até 2 horas, depois eu tô livre. A Mariana não veio para no campo?
So we can verify easily that this map is a simplicial map, because here I look at the one-dimensional simplex 0, 1. Its image, this is 0, 1, and it belongs to L, right? Counterexample, if K is this triangle and L is this two segments, then the map, let's say identity map on the vertices, is not simplicial, because the image of 1, 2 will be 1, 2, but 1, 2 does not belong to the simplicial complex L, okay? So this is not a simplicial map. Another example that will be important for us. Let's say I have a point cloud and the check complexes at time S and time T, S lower than T, right? Reminder, the check complex, this is the nerve of the cover given by the balls around each point, by the disks, right? So this will be the check complex just before the three balls intersect, and the check complex just after the three balls intersect. So the triangle here is not filled, and on the other side it is filled. And what map will I use? The inclusion map, the identity map between the vertices. And as long as S is lower than T, the inclusion map will always be a simplicial map, right? This is because when we increase the parameter of the thickening, the check complex, you add simplices. So actually the sequence of simplicial complexes given by the check complex is non-decreasing. So the condition here is always satisfied. All right. So let's have a look at how we can transform these simplicial maps in the world of homology. So I remind you that we defined last time the simplicial homology groups from the spaces of chains. The spaces of chains being this free generated group, right, on the simplices. That is, we allow to sum simplices. And you can very simply, from this simplicial map F, define a linear map between chain complexes, between the spaces of chains, right? And what you get is, so this sequence of this complex of chains of the first simplicial complex, of the second one, and now I have maps between this F0, F1, F2, induced by this simplicial map F, right? This complex here will satisfy a very nice property, that is the diagram commutes. When I say a diagram commute, it means that it does not matter the order of the arrows that I follow. For instance, if I compose the boundary here and the map F, it is the same thing as composing the map F and the boundary, right? So this is written here in this lemma. Simple to prove. And I can deduce from this fact that this map F will send cycles onto cycles and boundaries onto boundaries. All right. That also means, so this is a purely algebraic statement. If I have a map that sends one space into another and a subspace into another subspace, I can define an induced map on the quotient vector spaces. That is, these maps Fn induce a map between the quotient vector spaces. And if you remember last lesson, these quotient vector spaces are exactly the homology groups of our simple complexes. So purely algebraically, I was able to define from a simple map a linear map between the homology groups. All right. So it was just for you to have an idea of all this, how this construction works. So in the end, what I get are all the homology groups of K, of L, and linear maps between these groups. You can think as these maps are as follow. If you have a chain in K, so a sum of simplices, right? Epsilon being a coefficient, then the image will be the sum with the same coefficients, but then you take the image of the simplex, right? So how is that in practice? Let's say first that I have the same simple complexes. K and R are triangles. So H0 will be 0 over 2z, okay? The vector space of dimension 1, because I have one connected component. And H1 will be 0 over 2z also, because I have one hole, right? And in this case, I consider the map I consider is the inclusion. It's also the identity map. So this map will induce the identity between the homology groups. All right. So the identity between simple complexes induces the identity between homology groups. Another less trivial example. K now is a triangle and L is a field triangle. I also consider the inclusion of the first one into the other. So the first homology group here is still 0 over 2z, and the second one is 0. I have no H1 cycle in this. And so the induced map is the 0 map. Actually, it's the only possible map, right, between the spaces. I have another example here. K is still this triangle, and L now is the two triangles with a common edge. Okay. So what is the homology group of L? H1, it is 0 over 2z or 2, because I have two cycles, right? I have two holes. These vector spaces, I can use all the theory of linear algebra, right? I can choose a basis for the first space and a basis for the second one. If I choose as a basis for the second one, the basis formed by the first triangle and the second triangle, then the inclusion map will induce a linear map whose matrix is like that. Actually, there should not be a column here. It should be only one column, right? The first cycle is sent to 1, 0. Because it goes from a space of dimension 1 to a space of dimension 2. All right. I think I have a last example. K now is a hexagon, okay, 6 vertices. and L is a triangle. The map I consider, F, is the identity modulo 3. That is, I send the vertex 0 onto 0, 1 to 1, 2 to 2, and I send 3 to 0, 4 to 1, and 5 to 2. So I roll my hexagon twice around the triangle. These two simplicial complexes admit the same homology group, 0 over 2z, right? I have one hole in both spaces. So a question for you, what will be the induced map in homology? Do you have any idea? Let me put the chat. I will put the chat close to me, so if you have any question at some point, you just write. All right. So the answer to that question is that the induced map is 0. It was a hard question, actually. This is because when you follow this map, you roll the cycle twice, right? So what you get in the codomain, at the end, you get 2 times the cycle, right? And 2 times the cycle is 0 because in z over 2z, 2 is 0, okay? This could be understood as a phenomenon called torsion. But well, these kind of things can happen, right? And so, as I explained already, the category, the simplicial complexes form a category, and the homology is a functor, right? So you transform spaces, you transform maps, and you have this important functoriality property that says the following. If you have 3 spaces and 2 maps, and you consider the composition, you transform everything, and what you get in the end is that the transformation of the composition is equal to the composition of the transformations, right? And again, this is quite fast to prove. All right. So now we can go back to persistence. Let me recap what we've done. We have a point cloud, right? And we consider the thickenings of this point cloud. So what we get is an increasing collection of subsets of the Euclidean space. We will convert these subsets into simplicial complexes using the check complex, right? We take the nerve of the cover given by the thickenings. These inclusions, I will use a name to them, right? Instead of just writing the inclusion like that, I will call it I, T1, T2, okay? Because an inclusion can be seen as a map, right? So now I get a sequence of simplicial complexes connected by inclusion maps, and I will transform that in homology. So I obtain what is called the diagram of vector spaces. That is a sequence of vector spaces connected by linear maps. All right. And now, in this structure, I can start to talk about persistence. So let's select a time value, t0, and a cycle of the check complex at time t0. Okay, so I represented here the whole. I will define the depth time of this cycle as the supremum value of t's such that the image of the cycle is non-zero. Or it could be also the smallest value such that its image is 0. All right. I can also define its birth time as the smallest value such that it admits a pre-image, right? And the persistence of this cycle here will be defined as the difference between birth and death time. All right. So this cycle here does not have a large persistence, because if you increase a little bit the radius of the balls, it is 0. We have a cycle of higher persistence here. It is the big one, right? In order to kill this hole, you have to increase up to something like the radius of the circle, right? And these large persisting cycles, this is what will be interesting for us in a persistent homology. The idea being that cycles with large persistence will correspond to intrinsic, let's say, interesting, relevant features of our data set. They will represent actually homology of the underlying shape, while the short living cycles will be considered as topological noise. All right. This little cycle here, it's really an artifact of the way the points are sampled. And so what we can do to make this idea precise is we will create an algebraic structure that is called the persistence module, and this persistence module will mimic the whole construction we just did. So a persistence module is defined as a collection of vector spaces, okay, Vt, where T is a parameter in the real line, and for each pair of vector space, a linear map, VST, between Vs and Vt. And I ask two axioms. First, VTT, for any T, must be the identity map, okay? And if I have two maps, VRS and VST, the composition must be equal to VRT. So what is this? This is simply the functoriality property, right, of homology. And so our main example of persistence modules is what we've built before. You start from a filtration. A filtration, so this is a non-decreasing sequence of simplicial complexes, right? So you can think about check complex, Rips complex, but you have, I mean, a lot more different constructions of filtration that I'm going to show you a bit later. And from this filtration, you apply homology, and what you get here is a persistence module. Okay? So now we've defined a new algebraic object. The first thing to do is to define the notion of isomorphism, right? To be able to compare persistence modules. And the nice notion of isomorphism between persistence modules is the following. It will be a family of isomorphisms. So you want an isomorphism between each vector space. But this is not enough. You want to ask a commutativity condition also. You want that for every S and T, the composition of VST and phi T, phi being the isomorphism, is equal to the composition of phi S and WST, right? This implies that you preserve the structure of the persistence modules. All right. So now let's talk about decomposition of persistent modules. So I will consider two persistence modules here, V and W. what I can do is define the sum of two persistence modules, right? So to define persistence module, I have to define vector spaces and linear maps between these spaces. And the sum is simply defined as the vector space at time t will be the sum of the vector spaces at time t. And the linear map will be simply the concatenation of the linear maps coming from these persistence modules, right? If I have xy in this sum, I associate it to I take the image of x by the linear map of the first module and the image of y by the linear map of the second persistence module. And now I can talk about decomposability. I say that another persistence module U is indecomposable if the following is true. Each time that I write it as a sum, then one of those summands must be 0, right? So in other words, you can decompose non-trivially this persistence module, right? If I can write a persistence module as a sum of two other persistence modules that are not trivial, I say that the module is decomposable, right? So this is a very general idea of decomposability. What we do usually in math after defining what is a decomposition, we talk about the elementary bricks with which we will decompose the objects. And the elementary bricks of persistence theory are the interval modules. So to define them, I choose an interval, okay, of the real line. So it can be closed, open, or semi-open. The interval module associated to this interval is defined as follows. I take the vector spaces z over 2z, so the field, right, the vector space of dimension 1, if the parameter t belongs to the interval, or I take 0 otherwise. Here, this is my interval. Pink color indicates that I have z over 2z, and outside I have 0. And what are the linear maps that I will use? If my two parameters s and t belongs to the interval, I will take the identity map. And if they do not, I will take the 0 map. Okay, so this is a very simple persistence module. And they satisfy a very nice property that the interval modules are indecomposable. Okay. If I have several intervals, I can several interval modules, I can sum them, right? Just following the definition I gave before, the sum of these two interval modules will be this one. And by increasing the number of intervals, you get more complex persistence modules. And this is how we try to decompose, in general, persistence modules, right? But first, I'd like to give an important result. Now first, here I define the notion of decomposability. Given a persistence module V, I say that it admits a decomposition into interval modules if you can find a multiset of intervals of R, not T, here should be R, such that your persistence module is equal to the sum of the interval modules associated to these intervals, right? And so the first important result is, in this context, is actually a consequence of general results in the commutative algebra, is that if my persistence module admits a decomposition into interval modules, then the decomposition is unique. Okay. So I can talk about the decomposition into intervals. And this decomposition, I will give it a name. I will call it the persistence barcode of my persistence module. Okay. So as a remark, here I said multiset, because I can have several times the same interval in a decomposition, right? So this is a set with multiplicity. So let's say I have a persistence module and a decomposition into interval. I call this set persistence barcode, and I can draw it like that. I just stack the bars one on top of each other. There is another representation that is also used in practice, the persistence diagram. So instead of representing each bar, what you will plot are the points, right? A bar, an interval is of the form AB. You will instead plot the point of coordinates AB. So this will be a more compact visualization of the persistence barcode, because imagine if you have a lot of bars, it can be quite hard to read and plot the persistence barcode. But these are equivalent notions. So I explained that if you have a decomposition, then it is unique. But do we have a decomposition at first point? And the answer is yes. You need a technical condition that I wrote here. I will study only here pointwise finite dimensional persistence modules. That is persistence modules whose vector spaces are all of finite dimension. And then you have this very general result that says that indeed a pointwise finite dimensional persistence module can be decomposed into interval modules. Hence, it admits a barcode. And actually, there were already a proof of these statements 10 years earlier. So this is a very nice proof that actually only relies on the famous result of decomposition of finitely generated modules over principal ideal domains. This other proof is a bit more complicated, but it's more general. Right. Okay, so let me share an illustration. All right, so what I represent here is a point cloud and all its thickenings on the right. You can see the parameter T that increases on the left. And on the right are the persistence barcodes, right? So in red is H0, the connected component, and in green is H1, the holes. So how can we read these barcodes? Let's start with the first one in red. So in red, each bar indicates a connected component that is born at time 0, right? Because in the filtration, we add all the vertices at the beginning. And then when the bar stops, it means that the component died. So let's have a look. Let's say I stop here. You can see this bar here. I'm at the death time of the bar. So it means that I have a connected component somewhere that merged to another component, right? Connected components die by merging into another ones. And for instance, this will maybe correspond to these 2 points here that just merge together. So one of them dies, but the other one will survive, right? And you can see that you have a lot of high persisting components. Something very nice also that you can read on the barcode is the number of connected components that you have at each point in the filtration. For instance, let's stop here. You can see that I have 1, 2, 3, 4 intersecting red bars, right? So this means that I must have 4 connected components in my thickening. And if I verify here, I have 1, 2, 3, and 4. At some point, I only have 1 bar left. And so only 1 connected component left, right? So let's continue with the H1 barcode. This is the same interpretation. Each time I have a bar, it means that I have a new hole that appeared. So for instance, this one here must correspond to the hole here. And I know that it will be filled. It will die at the endpoint of the bar. So here, it just has been filled, right? I have some very small bars that must correspond to very small holes. Let's see, for instance, here I have 2 bars, and they may correspond to this little cycle here and this little circle here. What you can see, however, is the presence of 1 long bar, right? That starts here. And this long bar is actually the cycle represented by the underlying circle, right? And this hole persists way more than the others, right? Up to this point. Here it's filled. Actually, this is the general way we read persistence diagrams. When you have a persistence diagram like that, what you will do first is look at the long bars, because the long bars must signify something relevant concerning your datasets. Here, I have 1 long red bar and 1 long green bar. So my underlying shape must have 1 connected component and 1 hole, right? And which is actually the case here, since I have a circle. Do you have any question about that? All right. So let me continue.
DSA is okay.
So in conclusion, what can we read on the persistence barcode? First, we can read the homology at each step. If I stop somewhere, I know the exact homology of my thickening. But more importantly, I can see how it evolves, which features persist or not. And actually, the algorithm for computing the persistence barcode is basically the same as the one I presented last time for homology. you just build a matrix. You will, the boundary matrix, you will insert the simplices one by one, according to when they arrive in the filtration, and you do a Gauss reduction of this matrix. In the reduced matrix, you will be able to identify the bars of the barcode. All right. I'd like now to introduce the second foundational result of persistent homology, and this is the stability. So the problem of stability is the following. I still have my point cloud, X, right, that I consider as a sample of M. So here, X is here, and M will be the circle. I have the persistent barcode of the check filtration of my point cloud. How can I relate these persistence barcodes to the, let's say, theoretical, the ground truth persistence barcodes of the circle? The circle, it is a subset of the Euclidean space, so I can consider also its thickenings and its persistence module and its persistent barcodes. In the case of the circle, it's very simple because thickenings of the circles are anomalous rings, right? So it actually has the same homotopy type all along the filtration up to the radius of the circle, where it becomes a big ball, a big disk. So the persistence barcodes, direct barcodes of the circle are like that. One bar in H0 that lasts until infinity, and one bar in H1 that lasts until 1. So how can I compare these two barcodes? To do that, I will define a distance between persistence barcodes, all right? And this distance is called the bottleneck distance. Let's say P and Q are barcodes, okay? So multi-sets of intervals. This is Q on the left, P on the left and Q on the right. I will define first partial matching. So a partial matching, this will be a subset of the Cartesian product of the barcodes, P and Q, such that for every bar of the first barcode, there is at least, at most, one bar of the second barcode that is associated to it. Okay, two bars are associated, are matched if the tuple, the pair PQ belongs to the partial matching. And conversely, to each bar of the second barcode corresponds at most one bar of the first barcode. Okay. So with this definition, I mean, if my
so you're taking the biggest bar is the biggest bar, or
at this point I did not. I mean, you have several. You have several possible matchings, right? So this will be a partial matching. This will be another partial matching.
Yeah. Yes, indeed.
This will be the best one, actually, but I did not explain why already.
Okay. Okay. Sorry.
But when you have barcodes with a different number of bars, you have some bars that will not be matched, right? And these bars that are not matched, I will consider that they are matched with the midpoint, right? The midpoint of a bar is this point here. I consider the singleton and I associate the unmatched bar with the singleton. Now I will define the cost of a pair. Let's say P and Q are two bars matched together. The cost of this pair will be the infinite norm when I see these bars are as points of the plane. That is to say, the maximal value between the difference between the left extremal points and the right extremal points.
So you take the one with the minimum cost. Is it the matching, the best matching? Is
Yeah,
the one
yeah, yeah. But at this point, I just define matchings in general. I do not talk about minimization of the cost. So this is the cost of a match pair. If a bar is not matched, it is matched with its midpoint. And if you take the midpoint here for Q, you will see that this quantity is equal to the half length of the bar, right? And then the cost of a matching will be the supremum of the costs of all the bars, right? And now, as Stefanella said, what I'm interested into is the matching that produces the minimal cost, right? And this has a name, and this is the bottleneck distance, right? Between the barcodes P and Q. And in this case, this will be this matching. So basically what you want to match together are the most similar bar, right?
And yes, because I remember that there is this algorithm that calculate this. We were using as a black box so far. So eventually these two barcodes have a different number of components. So what do you do with the remaining points? So you match these two bars.
Yeah.
How do you compute the distance, this extra bar?
So what is the cost of this partial matching? You will have to look at the cost of all the bars. So the cost of this bar, or I must say this pair, this will be simply the difference between the extremal points. But you have also to consider the costs of these little bars that are not matched. And so you consider as a cost their half length.
The half length of which one? The big ones or the small ones?
The small one.
The small ones.
Yeah, yeah. For each.
So you first you match the optimal bar, and the remaining one you take half length.
Yeah, exactly. Yeah.
Okay, thank you.
And the thing is, the cost of the matching is the supremum of all the costs of the bars. So if these bars are very small, which is the case here, they will not count in the cost of the matching in the end, because the most important cost will be the two long bars, right? Yeah. So you can show that this is a distance. This is the distance between persistence barcodes, and we can deduce a distance between persistence modules, right? If I have two persistence modules U and V, I take their persistence barcodes, I compute the bottleneck distance. So now I have a distance between persistence modules, all right? So an example here, I took the barcodes P, only one interval AB, and Q is only one interval A prime B prime. Okay. Actually, you have two possible configurations. Either P and Q intersect, do not intersect, either they intersect. So what are the matching that exists between P and Q? You have the empty matching. It is when you do not match the bars, right? And so in this case, the cost of the bars will be their half length. So B minus A over 2 and B prime minus A prime over 2. So the cost of the empty matching is this one. And you have the second matching is when you match the two bars together. And so the cost will be this one by definition, right? The bottleneck distance between P and Q will be the minimum between these two costs, right? if I consider the interval modules B, AB and A prime B prime, then their bottleneck distance is this one by definition, right? All right, so I have now defined distance between barcodes. I could already state a stability result, but I prefer to go through a last definition that allows to make the theory works very well. And this last notion is that of interleaving distance. So you've seen this bottleneck distance. It is a distance defined at the level of the barcodes, not at the level of persistence modules. The interleaving distance is a distance at the level of persistence modules. So to define this distance, I first define an epsilon morphism between two persistence modules, V and W. And this will be a family of linear maps, phi t, now that go from Vt to W t plus epsilon. So I allow some kind of delay in my morphism, right? And these diagrams must commute, right? That is, this composition here must be equal to this composition. So this is a relaxed version of a morphism. And now an interleaving between this persistence module, an epsilon interleaving, will be a pair of epsilon morphisms, one from V to W and another one from W to V, such that these diagrams commute for every t, right? What does that mean? If I apply my first epsilon morphism and then my second epsilon morphism, what happens is I go from Vt to Vt plus 2 epsilon, and this must be equal to the linear map of the persistence module V, right? And same in the other direction. So that's the definition of an epsilon interleaving. And I can now define the interleaving distance between two persistence modules as the smallest epsilon, such that my persistence modules are epsilon interleaved. Okay? And so as you can see, this is an absolutely algebraic definition. I did not talk about persistence barcodes here, right? So let me take an example. I will consider the interval modules AB and A prime B prime. Okay. If you play around with this definition, you will end up with this result. I won't enter into the details. The interleaving distance between these two persistence modules is equal to this minimum. And if you remember, this is actually the same. This is also the bottleneck distance between these persistence modules, right? And actually, this is a theorem, the isometry theorem, that given two persistence modules, U and V, the interleaving distance is equal to the bottleneck distance, right? So this distance at the level of barcodes, that is very easy to interpret, is equal to this very algebraic definition at the level of at the linear level. And so the result naturally splits into two results: a stability result, the result that is called stability, and another one that is called converse stability. Actually, one of these results is hard to prove, and the other one is simple. The easy statement is the converse stability. If you start from the bottleneck distance, if you start from a matching between the bars, you can easily deduce an interleaving. All right. In the other direction, it's more complicated. So the first proof of this fact uses the interpolation lemma and other even more algebraic proofs arrived later. All right. So now I can put that in context and explain to you why this result is so important. So let's take two subsets of the Euclidean space, X and Y. You can think of X as our point cloud and Y as the circle, okay? And I will define the Hausdorff distance, right, between X and Y as epsilon. So alternative definition for the Hausdorff distance is that X is included in the epsilon thickening of Y, and Y is included in the epsilon thickening of X. And you can actually deduce that for every T, you also have these inclusions. The T thickening of X is included in the T plus epsilon thickening of Y, and conversely. Okay? So what can I do now? I first put my sequence of thickening of X on the top, at the bottom of Y, and I have these inclusion maps, right? I have a delay of epsilon for X to be included in Y, and conversely. And I will transform everything in homology. No, first I will take the check complexes. I take the nerve of the covers, and I obtain the same diagram, a sequence of check complexes of X, a sequence of check complexes of Y, and inclusion maps, right? I take this diagram and I apply homology, simplicial homology. So what I get now, you recognize the persistence module of the check complex of X here, and the persistence module of the check complex of Y. And what are these linear maps? Actually, these linear maps satisfy the definition of an epsilon interleaving. So what I obtain very directly from the definitions is an epsilon interleaving between the persistence modules built from X and Y. So I deduce that the persistence modules are epsilon interleaved. The interleaving distance is lower than epsilon. I use the isometry theorem, and I get that the bottleneck distance is lower than epsilon, right? And this is the stability theorem that has been proven already in 2005. If I have two subsets of the Euclidean space at distance, let's say two subsets, I build the corresponding persistence modules. In the case where they are decomposable, I have that the bottleneck distance is lower than the Hausdorff distance, right? So what does that mean in practice? It means that I can trust the persistence barcodes of my data, right? If I suppose that my point cloud is close to the underlying shape, I know that the persistence barcodes are close to each other, right? This closeness being quantified via the Hausdorff distance for the sets and the bottleneck distance for the persistence barcodes. And my whole presentation relied on the auxiliary notion of interleaving distance, right? which is now a distance between persistence modules. Do you have time to give a few examples, Stefanella?
Yes, I think we have still 5-10 minutes. 5-10 minutes. Mm-hmm.
Okay, fine. All right, so let me give you a few applications of these ideas on concrete data. And the first example is the cyclooctane configuration space that I talked about the first lesson. Remember, the cyclooctane molecule has 24 atoms, right? And admits different conformations in the space. And what you do, you transform the molecule into a point by gathering the Euclidean coordinates of all its atoms, right? So you get a point in R72. This point cloud, you simply compute its percent homology, right? The percent homology of its Czech complex. And you will obtain these barcodes. On these barcodes, what you observe are one long bar in H0, one long bar in H1, and two long bars in H2. And this actually corresponds to the homology of this quite non-obvious space that is the union of a sphere and a Klein bottle. And then you can use this information to actually study further the shape and observe this geometry. I also talked about these experiments of natural images. You take a lot of images and you extract 3 by 3 patches, subsets of images. With a lot of images, you get a lot of points in R9, right? And you apply persistent homology. And what you get are these barcodes, where you can read one long bar in H0, 2 long bars in H1, and 1 long bar in H2, right? So we deduce the homology groups of dimension 1, 2, and 1. So this can be, I mean, a lot of spaces admit these homology groups. You have the torus. In this case, this is the Klein bottle, right? These examples was the rats, the grid cells of the brains of rats, and you define a notion of distance between neurons, between grid cells, and you compute the persistent homology of this metric space, and you get persistence barcodes like that. So you have the same, you see the same homology as before. 1 bar, 2 bars, and 1 bar, right? And so this indicates the homology of a torus, and then you can study further and really observe a torus. So, right, these were very basic, direct applications of the theory. You compute the persistence barcode and you interpret it, and you hope to observe the homology of a known space, and then you can verify that it's actually the space that is underlying the data.
Or you can do something else. If it's not known, you can compare with some other parameter that might have identified similar structure. So you might induce some other information. You compare different kind of barcodes from, you know, your phenomena, and supposedly some of the parameters that might have a strong impact on your phenomena. They are shaping your phenomena. So it might compare.
Yeah, right. This interpretation is very the initial idea that you take the barcode and you hope to read the homology of the underlying space. Actually, with persistence barcodes, there are a lot of tools that they can use in different manners.
Yeah. I'm just saying it's not just recovering known shapes. It's
Yeah,
very
yeah.
rich. It's very rich.
Yeah, exactly. Let me give you an example of this actually. This cosmic web experiment. So Pearson homology is also multi-scale, right? The parameter increases, and you see you can observe different topologies. Remember that it's not clear what the dimension of the cosmic web is, or what scale we should use. It can be a bunch of stars, or also strings of stars, or it can be understood as clusters, right? What is the persistent homology of the cosmic web? And you can see this experiment here, right? So this is the persistence diagram, but it's put with a rotation. And you can see something very interesting. It seems like there are three behaviors, three patterns, and these three patterns corresponding to the three potential scales we can use to study the cosmic web, right?
One are the scale here. So how do you use the first to identify these scales?
So this is a simulated data. You simulate position of stars. You do the check complex. And then on the x-axis, this is the birth time of the topological features of the cycles, and y-axis is the persistence. Everything in logarithmic scale.
But how do you identify exactly the dominant time? You look at the peak, is it? You look at.
Yeah. So this will mean like at this point, you have a value where this is a density diagram, right? You have a lot of H1 features at this point, and then this decreases. And again, for some value, you observe a lot of H1 features again. And this will correspond to these in the three diagrams.
Thanks.
I will pass on this. Oh yeah, this Pearson homology. It's you cannot. It's not only usable on point clouds. You can use it on a lot of other structures. Here, I give an example on of image analysis. So this is a collaboration with Anton Francois that just presented his PhD a few months ago. And he works on a brain tumor. So glioblastoma, the brain tumor, that's a very important disease to study. And what you want to do is, given an MRI of the brain, to identify where is the tumor in the brain. And actually, this whole problem that is called segmentation, you want to have even more information. We would like to label the tumor in various components. You have the core, the surrounding tumor, and the edema. So what you can do is use persistent homology now for images. What happens is that the tumor, so it's not, you cannot see it here, but on MRI, the tumor will be very, will correspond to luminous pixels with high intensity. And so I can define a filtration of my space where I will add the high intensity pixels first, and then the low intensity pixels. And what happens is that the tumor is surrounded by this high intensity part. And so if I add first these pixels, I will observe a sphere. So this is the persistence diagram of my MRI, and this is actually H2. And you can see a sphere. If I extract this sphere, I get the surroundings of my tumor, and then I can get the other parts with what is inside and what is outside. And so in this context, we use another algorithm that is called cubic persistent homology.
So you're peeling the tumor.
Yeah, exactly.
Like an onion, like an onion.
Yeah, exactly.
Very nice, very nice. You should actually talk to the neuroscience that are working with images, Fatih Martal. They are trying to characterize the activation, so it's not tumor, it's activation or the brain when people are under stress. So maybe, so some parts are more intense. So in this sense, it will be, it could be related to your.
That would be
so that would be very nice if you can characterize if the same region or, how it might vary.
Cool.
Very
Let's
nice.
talk after that. Very quick, I will just talk about machine learning. So you can introduce persistence homology into machine learning pipelines. You can define kernels, right, between barcodes. What is more complicated is that barcodes are not embeddable in the Euclidean space. The barcodes are not vectors, right, because the number of bars does not have a limit. But you can manage to design kernels for barcodes, and you get interesting studies. You can also introduce persistent homology in neural networks architectures. So you have your usual neural network, and you will add this, what they call topological layer, right? That will add information. So H0% homology, right? You follow the evolution of the connected components, and you see when they merge together, right? And you can extract actually a more sophisticated structure from the H0. That is a dendrogram, where you can visualize exactly how the components merge together, and this allows to do hierarchical clustering, right?
It looks like a sort of phylogenetic.
Yeah, this is it. Yeah. And the last example, you can design a lot of very interesting algorithms with persistent homology, algorithms that can kind of take into account the topology of your data, right? And so, for instance, this persistence-based clustering Riemannian manifolds is an algorithm that allows, so you get this as a point cloud. It's a lot of noisy points in the space and 4 circles, right? So the result of a classical clustering algorithm will give that. And with this persistence-based algorithm, they are able to extract the actual 4 different circles. Yeah, you can also, so I said persistent homology on point clouds, persistent homology on images. You can do persistent homology on time series. How can you do that? If you have a time series, you can convert it into a point cloud with the famous technique of time delay embedding, right? A time series, so this is a sequence of values, and you will consider the points. You choose a dimension, n, and you will look at the vectors of n consecutive values, right? And so this gives you a point cloud, and you have theoretical results like Taker's embedding that states that you can read actually properties of your time series in the topology of the time delay embedding. So what you do is you have the time series, you embed them, and you compute the persistent homology of the point cloud. And this can give you very interesting information about the time series. Yeah, I think I will stop here. Let me just conclude. what you can remember from the whole construction is that Preston homology, right, offers a solution to the problem of homological inference, and yields multi-scale and stable estimation of the homology of the data sets. And yeah, this is it. Thank you.
Thank you very much. So let's thank Raphael for really a lot of information. It was amazing how you put together a very hardcore algebraic topology and data application. So thank you very much again.
Thank you.
And question. Thank you. Yes. Do you have any question? They're just thanking. So just to remind you once more that Raphael gave, I will put it again, I'm not sure I can copy. I'm not so good. Can you put again this reference here? I'm not so good in copying.
Yeah,
For the people. Yeah, for the people that enter later.
Yeah.
Yeah, so here I suggest this reference about TDA. So in addition to his wonderful notes. Okay, so I just remind you that next Thursday is the last lecture, unfortunately. And maybe who should have some computer nearby. Is it true or not? Yes?
Yeah. So this will be programming session. We will study together 2 examples. This will be on Python, Jupyter, on a Jupyter notebook.
So Kama, Daniel, Andre, just you have to have your computer with you.
Yeah.
Okay.
So I will write, please download.
And Daniel as well.
The library goodie.
So what do you good on your notebook? Okay.
You can just pip install goodie.
And I can use it on the Macintosh on my Apple. Yes. Yeah. Okay.
You use Python? You use Jupyter?
Use Colab. Is it possible? I might have Jupyter. They stole it to me. I haven't used it.
No, it's fine if you have Python. You just install the library without a problem.
Someone went through a lot of trouble to install Jupyter on my computer. I should be able to use it. Okay, so thank you very much.
Thank you.
Next Thursday.
Yeah.
Thank you.
Ciao.
Bye-bye. Ciao, ciao.